Hello everyone, I'm Devendra Kapadia, and this afternoon I and Adam Strzebonski, who's another senior developer, will be talking about what's new in calculus and algebra. We'll talk about new things in derivatives, limits, optimization, equation solving, and we also have something interesting to talk to you about online course development and college calculus. So thank you very much, and I look forward to seeing you at the talk.
So I will talk about what's new in calculus and algebra. It's a joint talk with Devendra Kapadia. And so here's the plan for the talk. I will talk about improvements for optimization and solutions of equations and inequalities. And Devendra will talk about enhanced derivatives, limits, integral summation transforms, and then about benchmarking, documentation, and online courses. So let me start with the first subject. So here are a few methods that have been added for exact optimization. So first is a pretty general method. It's variable replacement method for optimization of transcendental functions. So basically if we have composition like this, we can transform it into optimization in terms of variable replacing sign and one of the variables x or y, or actually y because it's here. So we have different two variables, and this way we can reduce this problem to solving polynomial optimization problem, which is something we actually have algorithms for. So for instance, this one works by this transformation, and we got a result. Here is a mean value. Also, so we can transform from xy variables to exponents of xy and cosine to x minus y variables with the appropriate transformation of the domain over which we optimize, and we get the max value. So another case that we have added are univariate trig functions with commensurable function arguments. So for instance, this is function of something and the function of 3 times something, trig function. So we can reduce it into one trig function of this argument and optimize in terms of this function over the range of the inner function. And this way we get the result of the optimization. There's rather complicated algebraic number, and max value of this function here, we get transcendental root object, but again we can recognize that this is the same argument, right? So this one is twice this, and plus 1 is okay, it's just translation. So again we can reduce to one trigonometric variable. So now, a little more complicated problem is, so we have several periodic functions with incommensurable periods now. So the theorem is that if inverses of the periods are linearly independent over the rationals, then we can treat them sort of as independent variables. So the set of values will be dense of f1, fn will be dense in the range of them taken separately. So for this to work, g and f have to, for instance, if they are continuous, it works. The more general statement is that the range of each function has to be contained in closure of the values at continuity points. So, and this is something we can check using the function singularity data that we have. So here is something. Here is one function. There is another one with linearly independent inverse of period, and here is the third one. And the mean value is this. So we can And okay, so this is the one that takes slightly longer, about 30 seconds on this computer. So here's the result. Gets quite complicated quite quickly. But it's doable. We get the exact solution. Here is the same kind of problem over the integers. So here, 1 and the inverses of periods have to be linearly independent over the rationals, and again, we can compute mean and max value in such cases. So max value of sine, that's easy. And here is, well, it's sine over the integer, so it's just sine of integer values, and the max value is 1, mean value is -1. That's the theorem. So they never quite reach the plus and minus 1, but the infimum and supremum are the same as if it was continuous function. Here is slightly more complicated case. So we have several of these functions, and we can also see that. So these are values at integer points. They're all above this minimum or infimum line. And here is a max value or supremum of such a function. And again, we can see that values of integers are we're going below the line, but not quite reaching the line. Another case, so univariate time elementary functions over the integers. So basically, these are functions that do not have periodic parts. So in particular, they will have finite number of roots and over the reals, and we can use them to solve the optimization problems over the integers. So these are basically by optimizing the univariate function over the reals and then taking the nearest integers to all the local optima. And here is a very easy case. So maximize minima of min and max. So basically, we can do all the arguments of min and max separately, and it's much faster than treating the maximum or minimum as a general piecewise function, which was what we have been doing in earlier version. So this took 25 seconds. Now it takes a quarter of a second. Now for some improvements in equation solving. So one of them is we can compute topological operations of on solution sets of real algebraic systems, equations of inequalities. So for instance, here is the semi-algebraic set described by one inequality. We can compute cylindrical decomposition, which means we can solve the inequality, get explicit description, and we can also get the explicit description of the boundary of this set. So here is the picture. So here's the whole set. Here's just the boundary given by these inequalities. And we can do the same for closure, interior, exterior, and we can do this for connected components. So here's cylindrical decomposition of the set, and here are the components separately. So we get a list of cylindrical decompositions of each connected component separately. So it's component 1, 2, and 3. Okay, and the second improvement is related to what I've shown for for solving of optimization problems with incommensurable periods. So here is we have systems of diophantine equations with coefficients that are not rational numbers. So earlier versions, we required that we have rational numbers in diophantine equations. Here we can now, since we have now developed technology to decide whether some set of non-algebraic numbers is linearly independent over the rationals, now we can use this to reduce a problem, diophantine problem with non-rational coefficients to a system of problems with rational coefficients. And here's an example. This single equation reduces to composition of Pell equation with linear equation, and here's something we have complicated. One complicated equation reduces to a system of equations that's actually quite easy to solve.
Thank you, Adam and Roger. Okay, I'll talk about some calculus improvements. And basically, last year, Roger said that we should drive back activity into calculus. I mean, calculus has been our strong point forever, but we just wanted to get back into this kind of the act of improving the major functions, d and limit. I won't mention the other one, which everyone knows, that's integrate. But we wanted to really start making improvements to the existing functions, and we began with derivatives in version 11.1. So we added the nth derivative of various things, beginning with, let's say, sine x. And so that's a formula for the nth derivative, depending upon the index n over here. And you can check that it agrees with your intuition in the first few cases. So nth derivatives have been studied by various people, but they were not in the system, so it wasn't too difficult to put the table in and then do some other work on top. So as soon as I did that, Adam said, oh yes, I can make derivatives go faster with this method. So he basically used the nth derivative to make the actual derivative computations for high orders go fast. So here's the billionth derivative of sine x done instantly in version 11.1. It took forever early on. Not that this particular example might be important, but shows that you do something and you build on it. And then, meanwhile, Oleg came along and talked about the Leibniz rule and the chain rule and stuff like that. So we had nice formulae very soon for the product rule that looks formidable. But if you just let n go to 1, it's just the product rule from calculus. And similarly, we had the chain rule, the Fade-Bruno rule that they spoke about right now. It's got Bell-Y in it. And again, if you put n equal to 1, you get back the chain rule from college calculus. So all that looked very nice and algebraic, but my worry was there's nothing geometric about these things. You somehow think of Taylor series being very boring compared to Fourier series, and that's been the impression. But recently, Michael Trott pointed out to me that Michael Berry actually had a very nice paper where he said that the higher derivatives of a function produce oscillations. What does that mean? So here's an example. Here's the nth derivative of Gaussian. And if you plot the higher derivatives, you can see I'm going from 0 to 10 to 30 to 70. It goes quite fast because I've got these hypergeometrics over here. Then when you do that, you actually should see some oscillations. So in a sense, Taylor series are very similar to Fourier series, with the higher terms, which you normally neglect, being like the higher Fourier harmonics, which get thrown away in any approximation, which is a very nice viewpoint on nth derivatives. And it only came about because we did nth derivatives over here. Okay. Meanwhile, Roger realized that there are these so-called holonomic sequences. So that's something he worked on for version 7. So for example, Bessel J is holonomic in n. And what that means is that it satisfies a recurrence relation in that variable. So in earlier versions, if you found the high derivatives of Bessel J, they would just blow up because we didn't use the recurrence over there. So you'd go up and down, up and down, up and down, and you'd get a huge mess, which could even blow all the memory on your machine. But now you get back this beautifully compact answer for the 10th derivative. And Maple doesn't, so that's good always. Okay, so finally, something that really affects our users. So for a long time, people have kind of observed, complained, whatever, that we could not differentiate with respect to indices. Let me give you an example. So here's a function f of an index variable. You sum it. You want to find derivative with respect to x5. And that looks easy, but it's very hard to actually carry it out in practice. So Now, Itai and Jose, who know about tensors, got together and actually did a very nice job of doing the derivatives of these things. Okay, similarly, you can do inactive stuff, which is very useful because if you did that actual sum, it would blow up, and you get back some nice answers. So basically, derivatives have become much, much nicer in version 11.1. And then in version 11.2, we decided to be a little more serious about a particular set of functions and focused on limits. And so Adam rewrote the limit function and implemented the so-called Grund's algorithm. That's a huge example which looks like it should give infinity, and it does in version 11.2. If you try it in earlier versions, it just hangs to my knowledge. We also have max and min limits, pretty useful. That's a very simple example. And we actually can go quite hard on the examples over here and get very complicated periodic function like Adam showed to get the max and min limits. Okay, the really big breakthrough was multivariate limits, which we've been trying forever, but it finally worked out. So here's a college textbook example. You have a function of two variables. You plot it. The limit depends upon the direction which you approach the origin from. So you try it along some lines. You get different values. And that says that the limit does not exist. So multivariate limits are completely new in version 11.2. We have tested them against all the standard vector calculus textbooks. And this week, Adam is testing them against 1,000 examples more. He, I think, got to number 890 so far, if I remember it right. Okay, and finally, discrete limits, another nice area. Sequence limits, which people have requested early on. So here's what we call a densely aperiodic sequence. It oscillates widely. And of course, the limit doesn't exist. The discrete limit, which is a new function, the sequence limit doesn't exist. However, you can still compute the max limit in the discrete case using Adam's technology for maxima and minima. And you can also compute the min limit. So basically what we have is a very nice improvement for limits all over the place. And we have a talk tomorrow where I'll actually discuss the results of a large benchmark with 1 million examples. We ran it with version 11.2, with Maple 2017 and SymPy. And of course, I'm speaking about we've probably done very well. So I'll show you tomorrow that actually we have a nice limit in version 11.2. That talk is tomorrow at 4:30. Okay, on the transform side, we have nice improvements for periodic transforms, which Roger observed are easy to do because you can reduce your transform to a finite interval. And here's a Laplace transform example, which would actually be impossible early on. That's a plot of the Laplace transform for complex arguments. The Z transform is much faster for multivariate inputs. That's important for future. We also have the Hankel transform, which we introduced kind of pure mathematically because it had to be done. Maple has it. But then we realized that, in fact, it lets us do two-dimensional Fourier transforms quite nicely. So here is a two-dimensional Fourier transform that works very nicely in version 11.1 thanks to the Hankel transform. So now if we do it over here, you see you get the Fourier transform back quite quickly for a 2D function, never possible before. And that's all coming from a Hankel transform evaluation. Okay, so we did the Hankel transform, and then the question was what remains? Well, I had wanted to do the Radon transform for a long time. That's the one that determines the mathematics of the CT scans that people go through. And so the idea is very simple. You have, let's say, a section of your body, and you want to do a CT scan of it. So you send rays or whatever from various directions, and then you want to reconstruct the image reconstruction, and that's what the Radon transform does. And that's a hard problem to do directly, but even harder to do in the inverse direction. But we had the Hankel transform. Hankel gave us 2D Fourier, and then 2D Fourier has given us Radon. So we have kind of written on each wave to get to the next level. Okay, And here's a nice plot. So basically, when you do a CT scan, the machine would get this picture, and then it would reconstruct the original image from that. And finally, I go on to where my heart really has been for the last 1 year, that's education. So we've always been kind of on the forefront of education, but Roger said, why don't we try and actually do a complete calculus textbook with the Wolfram language of Mathematica. So I had interns working through the last summer, this summer. They finished a month ago. And now we have a complete solution of this book by Stuart, around 5,300 examples. Stuart's book is quite popular. He made a fair amount of money on it. He built a house worth $28 million, something of that sort, with that money. It's called Integral House, fittingly. And so now we actually have under our belt the complete solution manual for James Stewart's book for our own education. We are not planning to share with anyone at the moment, so this is purely private, but it's got every single exercise solved from this index. You can just go in and get to every notebook. There are lots of them. And here's sample notebooks. In fact, when Parikh was working on this, we had to solve differential equations with series solutions. I was working on it. I gave him my function, and so we have asymptotic desolve, which we'll talk about tomorrow morning in a talk with Adam on asymptotic expansion. So what we've done is to use current functionality and future functionality to come, some of this just solve the whole book. We've done it all. It took a long time, but I'm confident we have done this. So that, I think, is really a nice achievement, thanks to all our wonderful interns and Henry and people like that, and who really work hard. We've done lots of work on the documentation side. Itai has worked hard to make the D pages better, the limit page better. Coming up after that, so D is now a much nicer page, more scope, more applications, more college calculus applications. And coming up, integrate in version 11. So we had D in 11.1, limit in 11.2, integrate 11.3, sum in the version after that, some convergence in the version after that. And meanwhile, we also added probably 2,000 examples to the page for special functions. We've done 100 of them. We'll do 150 more in a few months. And so you should have pretty much a complete refresh of all calculus documentation in the next 1 year or so. And one last point that if we did all this, my question, what to do with it? So, well, I had an intern this summer, John Clark from Caltech. He joined me, and we worked together to produce a full Introduction to Calculus course with the Wolfram language. So John did calculus in the 7th grade on his own, passed the AP calculus in 9th grade, went to Caltech, and finished up his degree. And he told me that, at Caltech, they tell us what to do, not how to do it. So this is basically his work, and we now have a complete course lineup for Wolfram U Calculus, which should get recorded probably in December or January, something of that sort. So it's got everything you would expect from a standard calculus course from the Wolfram language point of view. So just to show you a sample lesson, here's the first one. So that's the first lesson, what is calculus? So it begins with calculus science of change. What are the 4 main problems? Tangent to a curve, area and length, velocity problem, optimization. What's the pre-history of calculus? Well, here you are, early development. And then question is, if all that happened before Newton and Leibniz, what did they do? So real controversy is, did Newton and Leibniz really discover the calculus? And that's a subtle question, okay? And we discussed that over here. In what sense are Newton and Leibniz the discoverers of calculus? Going on further, what happened after them? How is calculus used today? Why study it? What's the course about? Who's it for? Well, it could be a little girl from middle school, or could be a professional with no time at all, or anyone who loves to do calculus in Wolfram language. So this is a complete course for calculus, which should come up hopefully sometime in the next year and be available to everyone on the web. Okay, so to summarize, we have been focusing on very concrete things recently, core areas of calculus and algebra. The next step, we go into asymptotic expansions, series solutions, etc. And of course, we keep on driving education. So that is the summary of my talk, and I thank you very much for listening. If there are any questions, I'll take them now. Yes. Thanks.